Hello and welcome to Sigrity's webcast today. Our focus is on layout checking for SI performance. Our speaker today is Joy Lee. Joy is a Sigrity product marketing manager whose focus is on our C2000 product for time domain signal and power delivery system analysis. We will take about 1/2 hour in this webcast, and if you have questions, please send them in via the chat window. You can do that by pulling down the screen at the upper middle. With that, I'll just turn it over to you, Joy.
Hello, everyone.
Looks like things are a little frozen for Joy at the moment. Moving the slide, somehow locked up. So bear with us for just a minute while we get this figured out.
Okay, sorry for that. Today we will cover 4 parts. First, we'll start with a look at the complicated relationship between the layout SI design and layout design rules. And after that, you should be very much interested in the layout checking feature where we'll introduce those are SI performance metrics checking and the case impedance coupling checking. We use a DDR data bus as demo. In the end, we'll see how those 2 layout checking features work together for layout SI assurance. In a typical design, the system requirement is used to produce a set of design rules for the layout. Layouts supposed to follow those rules. So where is the problem? The problem is that the SI performance is a collective, combined, and electro-based quantity, while the design rules are multiple individual geometry-based. From a design rule to SI performance, the relationship is very complicated. Like they are in a different world, just not just only across the Pacific Ocean. Design rule is binary. It is a yes or no. Mostly yes, sort of yes is not acceptable. Well, the performance is analog. It's how much. Is that good enough? Good enough, in most cases, is far better than the best. Geometry-based design rule check has many limitations. First, not all design rules are absolutely necessary, or at least, we don't think so. Because for one reason or other, those design rules tend to be conservative. On top of that, not all layout factors affecting SI performance are covered for a practical board. For example, the via-to-via coupling, non-ideal power ground effect. The most confusing part is that the impact of one or a few rule violations is not clear. And there's no information available for design rule trade-offs. Just because design rule is binary, it is a yes or no. There's no gray area, there's no design freedom for the layout engineer to handle the complexity and the cost pressure of today's practical board. So, what is the alternative? The alternative can be simulation-based design verification. Starting from single and a coupled line-based simulation. And this type of simulation is easy and somewhat better than the design rule check. But the non-ideal power ground effect is not included in this type of simulation. If that effect is important to you, and then this option falls a little bit short. The next level is broadband model-based simulation. This is better if done right, but this is hardly practical for a full board. There's also general 3D EM time domain-based simulation, and I probably made a mistake to put it there because those are not supposed even considered as an option as far as layout is concerned. What we can see is a gap in the middle. We need something to be comprehensive enough to include all layout factors affecting SI and practical enough for a full board checking. Quick look is coming. What do we want? What we want is a simulation-based design check for the layout engineer. What we want is for this electrical check to cover all of those things. It's a layout-based time domain simulation. It's practical enough for full board. Consider all the major layout SI effects. It's simple to use, easy to set up, generate a report, and have a simple performance indicators so that we can compare one design with another, and can be run by layout engineers. Then this would be a big step forward in layout SI engineering. Which tool has this capacity? You probably guess where am I going? It's a Speed 2000. Speed 2000 is industry's one and only layout-based time domain field solver, taking into account all major layout factors affecting SI, such as trace impedance, recent path discontinuities, the coupling of a trace via the plane's non-ideal power ground effect. Major applications for Speed 2000 are power ground noise simulation, real SSO simulation with epic model to consider non-ideal power ground effects, EMI simulation with far and near field radiation simulation, TDR-TDT working as a virtual scope, and the newly developed layout checking. And this is why we're here today. The first part of layout checking is SI performance metrics checking. SI performance metrics checking, which is the gap between the design rule and its SI performance from electrical domain to the geometry domain. It does everything on this list. There are main three things about SI performance metric checking. It is comprehensive and practical for board level electrical design check. And it's easy and fast to set up. How easy? Now we have an example here for you. With the memory channels, one CPU, 4 memory controllers, 8 SIM, 420 nets, the setup time is 3 minutes with 8 automatically generated net books. The reason it is easy and fast to set up is because we use the simple source and termination models, and we also automatically generate net groups for different interfaces. The result of the SI metric checking has 3 main parts. One is the waveform, the transmitting, receiving, fine crosstalk, and near-end crosstalk waveforms. They are nicely bundled together. and SI performance metrics using the received and found crosstalk waveforms are nicely listed in the table, and you can sort that table, and nicely generated checking report. This report has the files and the setup and the results and everything. It's a complete recording of the checking activity and its results. And this is something that you can bring to your design review meeting, you can send to your managers. Net group. What is net group? Net group include a group net that they share the same transmitting and receiving components and the circuit models, and the nets belong to the same interface. In net group generation, associated nets and the differential pairs are automatically detected and handled for the user. One net between the two components are considered as one signal. One differential pair is considered as one signal, and one pair of associated nets connected by a passive component is also considered as one signal. In a checking simulation, multiple net groups can be checked in one simulation so that you can see the couplings between the different interfaces.
Okay, Joy is switching now to a demonstration, and is that right, Joy? Yeah. Yes. And I'll just remind everyone, if you do want to send in a question, you'll do so via chat. Up in the middle of your screen at the top is where you'll find a pull-down window for chat. So you're now in application, Joy, right?
Yes. This is the SI performance metrics checking. The results are nicely bundled together. RX results. Received waveform is red. Transmitted waveform is green. Star and crosstalk, and near and crosstalk. This is the first thing user will get when they run checking simulation. After this, a report can be generated in just a matter of a few seconds. This is the report. Report has the date and the version of the software you're using, where the files are, backup. We tell you a little bit about SMS checking, how it's set up, and what the result is. We're going to start right here. TX and RX waveforms are obtained by running simulations of one net, assuming all others are quiet. Well, the near end and the far and crosstalk waveforms are obtained with the target net as quiet, but all others are active. That's how we got those four groups of waveforms for every net in the net group. From those waveforms, the performance metrics are calculated using RX waveform and star and crosstalk waveform. The integration of a signal is an indication of how much signal we have. Outside of the signal is ISI. Crosstalk is the combined crosstalk from all other nets in the same simulation. Based on the signal, ISI, and the crosstalk numbers, signal noise difference is defined as well as signal noise ratio. Those five performance metric numbers will be listed in the table, in the report. The report also shows what is net group, the name of the net, the TX and RX components, and the relative position of the components and the routing. It shows what type of a circuit the pulse is used to generate in a simulation resources used, and the results.
Actually, we've had a couple questions come in, if I can go through a couple of things quickly. So one person is asking what the starting point is for this. So you've taken a layout database and brought that into C2000, right?
Yes, layout database and brought into C2000.
Okay, and you can see this on the screen just with the checklist workflow for layout setup, and
yes.
then you started the simulation, and this is the report that's automatically generated, right?
Mm-hmm.
Okay, great.
Have technical difficulties.
Okay. Well, if I give you a chance to ask you another question. So the design that you're showing, maybe you could just tell us a little bit, because I know you didn't run the demonstration live because of time. Can you just tell me like what the size of it is and what the runtime would be? And then someone is asking, what if there was a design with a lot more signals being evaluated? Maybe you can comment about that.
Design with a lot more. This feature is developed with the whole board screening in mind. The designs with a lot of signals running, and what we suggest user is to divide this into different different net groups, and run the same type of net groups together, or run the different interfaces net groups together if you want to see the interaction.
Okay. Okay, fair enough. So another person, and I know you have some other material you're going to go over. So are we going back to the slides now? I'm trying to think if I should ask you this other question or wait a bit.
I have a little bit technical difficulties, and the layout checking results is not shown here.
Okay.
Okay.
So are you headed back to the slides?
Yes.
Okay, let me ask you a question first while you're setting up to do that. I had one person write in to say that they are already a user of C2000 and that they thought of it as a tool that is really focused on the department that does signal integrity analysis. Is this checking capability more for mainstream users or these experts?
This is targeted for lower-level SI engineers and the layout engineers.
Okay. So still the existing applications would be the purview of the expert team, but this new application broadens it so others can get the benefit.
Yes, this application will lower the entry level for C2000.
Okay, great. So there's a follow-up question on this starting point. Someone is asking what databases the tool takes. So it's really all of the popular ones, right?
Yes.
Cadence, Mentor, and so on. And this is a board-level example. Could be used for packages, but probably more often boards.
Probably more applicable for board, because this is a layout-focused checking tool.
Okay. And then the same person is asking, does the tool use a field solver?
Oh, yeah. This is a time domain field solver, the one and only.
So actually, it's all the smarts of C2000, but now with a use model for checking that includes a lot of automation.
That's correct.
Okay, and someone else is asking a specific question about a DDR design. He's asking, for example, if we want to check DDR nets, do we need to select the DDR nets, or is the tool doing that automatically?
The tool works like if you want to check DDR nets, you select one component as a controller component, and you select one memory component. We will find out all the nets between the controller and the memory, as well as find out if you have more than one memory devices, we'll find out all the rest of the memory devices. And when we do this, if you have a server board, let's say thousands of nets, it is immediately reduced to a couple of hundred. And also those nets found are nicely bundled together, so you can select which one you want to simulate.
Okay, and actually, Joy, it looks like the slide that you're on right now amplifies on this point a little bit. So maybe we'll take it from here. There are a few more questions. I'll circle back to some of those in a little while.
Okay. Sorry for the performance metrics didn't show up in the report, but the performance metrics are those integration numbers, and they can be used to screen the board and identify the worst case for further analysis. And they can also be used to investigate SI impact of design rule violations and the trade-off options. And this performance metrics can be used to compare with the known good design or part of the design that has been fully analyzed or a reference design. This is one example. We have 16 nets ranked using signal noise difference from high to low. And with that net order, we also plot the signal noise ratio as well as all three other performance metric numbers: integration of a signal, integration of SI, and integration of crosstalk. And this shows that for this 16 nets, the performance ranking is dominated by crosstalk. The net 15, with the most crosstalk rank lowest in performance. Now I'm about to move to the next checking feature, which is the trace impedance checking.
Okay, actually before you do, maybe we should circle back to a couple of these questions. One other person is asking, how are the sources set up? For example, looking at rise time and voltage swing.
Source are simple voltage source. They are one pulse, one trapezoid pulse. And you can also, the source circuit, you can just put a simple resistance or RC parallel, RC serial.
Okay.
And you just fill out the table, and that's it. So that is why this setup is really fast. And then also you can save the circuit and have export your checking circuit or import the checking circuit if the reference design is done that way.
Okay. Okay, great. So there are a couple of other questions, but maybe we'll go into the next set of checks you're going to talk about a little bit, and the questions that have come up are now more general. We can handle those more at the end.
Once the SI performance checking shows that a few nets falls short in terms of SI performance target, now the question will be, what is next? How do we fix it? Why is that happen? Just like the previously shown the net 15. Once again, what do we want? It would be nice if we have a comprehensive DRC, not just a simple DRC, and this comprehensive DRC gave us, they will check impedance and coupling, report the trace length, number of V's, number of return path discontinuities, number of trace over void, and give us high-level result summary for sign-off and review, and a detailed and interactive results for debug, and easy and fast to use for layout engineers. And a feature like this would give us a great insight into layout and its relationship with SI. That is our trace impedance checking. Trace impedance checking gives us everything on that list with collapsed, expanded plot, summary detailed table, layout overlay, and the plot to overlay cross-probing. It is a great debug tool.
Okay, great. I think, Joy, we're going to give a go at the demonstration of this capability, but while you're queuing that up, there was a question that came in on how Speed 2000, how is this tool different from PowerSI? So I'll quickly say that Speed 2000 is operating in the time domain, whereas PowerSI is a frequency domain tool. And someone else is asking about what release of Speed 2000 has this new checking feature. The first step, maybe you'll comment on that, and also maybe on what's in PowerSI with respect to releases.
The trace checking feature is available from 11.0, and SI performance checking is available for 11.1.
Okay, and 11.1 is in beta now for Speed 2011 0 is in production.
Yeah.
So with that, let's jump into this other capability, Joy.
But this is the trace layout check, trace impedance coupling checking. We have a lot of results, and they're in different forms so that users can get what they want. Impedance summary table. And by net, we have a number of sections without reference, number of trace sections with reference feed continuity, number of vias, and the maximum impedance, dominant impedance, minimum impedance, and the trace length, a lot of things. And correspondingly, we also have a coupling summary table, the impedance plot. We have an impedance plot, and this we call that the collapsed impedance plot by net, and this one is great to show the impedance distribution. And impedance expanded plot shows the trace length, and then by net you can actually see which net is doing what. Detailed impedance table has everything. The impedance for every trace segment. There's a lot of information here. Hopefully you never have to go to this level of detail, but just in case you do, the information is there. Impedance overlay in layout. The trace is color-coded with the impedance value. And impedance, now when we check, when we show that in plot or overlay, whatever we do is relatively boring because layout tools, they do control impedance reasonably well. Therefore, what we show is boring. Higher impedance is in the component breakout area. Once you go outside, and as we can see, impedance control reasonably good. But in terms of coupling, it is different. It's all over the place, become a whole lot more interesting.
So perhaps you could describe what we're seeing here, Joy. It looks like there are a couple of outliers in the upper left. Is that?
Yeah, those are the high coupling. The coupling coefficient, and these are nets. This shows you distribution. And we also have expanded coupling coefficient. You can see that the trace length is shown, and the location of a via is shown. That is a via, and that is the end of a via. And this line is color-coded with its coupling coefficient for each trace sections. And detailed coupling coefficient table, there's a lot of information. Once again, you probably do not need to go there, but just in case you do, information is there.
Okay. And actually, if I can ask you to pause for just a second, I have a person asking if you could explain a little bit more what the coupling coefficient is.
It's near and coefficient.
Okay. Okay, great.
And coupling coefficient in layout overlay. So the layout trace is color-coded with the coupling coefficient. That where you have more coupling, it shows immediately. And cross-coding is that if you find out a certain trace, click this, it shows up in the layout. It's this one. And also in plot, if you just move your cursor on each every section, you will see which net this is and which trace section it is. Once everything got more crowded, it's kind of hard.
So the idea is you work to improve the design on the areas where that effort will make the most difference.
Exactly.
Yeah.
You know where to focus. I'm going to get out of this demo mode. Go back to this mode.
There's another question that came in asking what is the range when coupling is calculated? And I'm not sure I'm understanding the question. Is it clear to you? If not, we can get back to this person offline.
I will take a guess.
Okay.
In the simulation, people usually define a range of a coupling to consider to manage the complexity of their simulation, which means below a certain coupling level, those will be considered as not coupled, just to be able to manage their simulation. But in the checking, because we don't have to run simulation, we check everything. If it's low, we tell you it's low. Just like in the checking the distribution plot, right? There's a lot of trace, their coupling coefficient is zero, which means the bottom line is very fixed.
Okay.
Since there's no simulation considered, no model to be generated, we don't care. If it's low, we show you it's low.
Okay. Fair enough. And there's that same person has a couple of other questions, so we'll maybe get back to some of those offline. Why don't I let you continue on?
Now that you know something about our layout checking, one is SI matrix checking, the other is the trace checking. How do they work together? Let me show you two examples. This is one example. In this particular SI matrix checking simulation, we found out that everything, by everything I mean all the waveforms and the performance metrics numbers showed that one group of signals is far worse than the other group of signals. And when you look at them, they honestly look the same. And then when we looked a little bit closer, we found a small piece of plane underneath this group is missing. And that's why this group's performance is bad. This is one example. The next example is that we checked some data bus. And DQ15 is the lowest ranking data. And the far and crosstalk waveform shows that DQ15 has the largest magnitude of far and crosstalk waveform, compared with the best one, DQ5, this one. And then we ran the trace checking. We found out that DQ15 is this trace. From here all the way, this is the memory controller, and all the way go to the DIMM. And you can see that color-wise, this one is a whole lot redder than DQ4 or 5. These are the better performance net. Once again, the performance for this particular data bus is dominated by crosstalk. These two examples are not hard to understand. This is not high-tech, but they are very hard to single out. If you have a board with hundreds and thousands nets, if you look at this board, you look at the net, and you look at the plane, it gets dizzy pretty fast. So this is where the layout checking value comes in. We single out the potential problems for you to take a closer look. You don't have to do the finding. Now that we have introduced the two layout checking features, the SI performance metric checking is a layout SI level macro view. It's electrical, all-inclusive end results. It shows what happened and its effect on performance. This feature is great for screening, review, and sign-off. Trace and coupling checking is layout SI micro-level view. It's individual in the geometry and it's a segmented results. It shows why a certain low performance happens and how to fix it. This is great for design and debug. In conclusion, SPI 2000 is industry's one and only layout-based time domain field solver. All major layout factors affecting SI are considered in SPI 2000 simulation. SI performance checking and trace impedance checking are complementary pairs of layout checking features that provide great insight into layout SI performance. And it saves time for seasoned SI engineer because layout engineer and new SI, lower level SI engineers can use it. The next question is, how can we help you?
Great. So we can certainly handle things as follow-up that relate to specific design. There are a couple of questions that have come in before we wrap up, so we'll get to some of them. I'll kind of stay with the time that we allotted for this. So Joy, one person asked that you showed an HTML report for one of the types of tests. Is an HTML report available for each of the things you showed or only some of them?
Report is for SI metrics checking.
Okay.
The report for trace impedance checking is being developed.
Okay, okay.
Not
so
ready
in the
yet.
current version, they'll get all of the feedback within the tool, and in the later version, it'll be available also to share with colleagues in HTML.
Yes. But for trace impedance checking, even though we do not have a nice-looking report, but we have a lot of Excel data output so that you can process them any way you like.
Okay. And then for a person who is already using SPI 2000, if they're going to do the trace checking on a design that they've already run some simulations on, is the simulation runtime about the same as for the same design as another SPI 2000 run?
Trace impedance checking in SPI 2000 is way faster than simulation. Because when you run simulation, you have to match the plane, match everything.
Okay.
But in checking, it's not even called simulation, it's called calculating. We calculate the trace coupling coefficient and we calculate the impedance, but we do check the planes to find out where the reference is, whether or not the reference is changing, we do count for the phase length.
Okay. Okay, so we had set a time here for a half an hour. We've gone a bit over, so I'm just going to grab one more question and then we'll wrap it up. So this is a little bit going back to some of the detail for the DDR design. So someone is asking, how does the tool set the data rate for a different interface in the checks that are being done?
Data rate is reflected in the stimulus pulse width.
Okay, so is there a place to enter a value for that?
Yes, it's in the table.
Okay, okay. And actually two others because they're short. One person is asking if the tool can check for differential impedance.
Yes, we can. But the trace impedance coupling checking, the current version, we check single ending impedance only, and the differential impedance will be in next release, which is 12.0.
Okay, okay. And that will be early in 2012 is kind of when
That's correct.
Thinking about that. And then I'll take, I think that's it. The last question came in twice, so we'll leave it there. I will capture the questions in case we didn't get to some. I think there were a couple we didn't get to, so we'll circle back to people on that individually. I want to thank everyone who participated live, and certainly I thank you also, Joy.
Thank you. Thank you for coming. Let us know how we can help you.